This is going to be lesson 2 of structure and bonding. So in this lesson we are going to look at polar molecules. That's the last section in the subtopic types of chemical bond, although really what it relates more to is the next part of this topic, which is all about intermolecular forces. So we're going to start by looking at polar molecules. We're then going to look at London dispersion forces, which will be a bit of a recap, and then we're going to look at something called permanent dipole interactions. It's a bit of a mouthful, quite a long one to write down, but hey, that's chemistry for you. We love using slightly long words. So when you're working through this lesson, you'll need to make sure you've got your data book with you, because what we're going to be looking at quite a lot is this thing called electronegativity. I'm going to start with a little starter question for you, just to make sure that you have a good understanding of the previous section on covalent bonding, because all of this stuff on intermolecular forces and polar molecules really relies on you understanding the previous section on covalent bonding quite well. So your question is nice and simple. What is meant by, first, a pure or non-polar covalent bond? What is meant by a polar covalent bond? And if we've got a covalent bond, how do we know whether it's going to be pure or non-polar, or whether it's going to be a polar covalent bond? Pause the video now and try and write down some answers to this before I go over them. Okay, I'm really hoping you got this, because most of those work I've seen, you all did a good job of this section in the notes before. So, a pure or non-polar covalent bond is one in which the electrons are shared equally. So, equal sharing of electrons means there's a pure or non-polar covalent bond. Another way of saying that is that there's no permanent dipole or no bond dipole in that bond. A polar covalent bond, on the other hand, is where we have electrons shared unequally, and this leads to a permanent bond dipole. And we quite often show that by putting in those little symbols, delta plus and delta minus. So what happens is one of the atoms is a bit of a greedy atom. It's going to hog the electrons. The electrons will be shared unequally. The greedy atom, which is hogging the electrons, is going to become slightly negative, because electrons are electrons are negative, so it's going to be slightly negative. The other atom, which is less greedy but is getting the electrons stolen from it, because it's going to have fewer negative electrons spending time around its nucleus, it will become slightly positively charged. So how do we know which one we have? Well, the measure for the attraction an atom has for the bonding electrons, or in other words, how greedy it is and how much it likes to steal the electrons, is its electronegativity. So a bond will be polar, a covalent bond will be polar if there's a difference in electronegativity between the two atoms in the bond. So we've had a look at polar bonds. And we've looked at different types of bond individually, so we've just considered the electronegativity difference between two atoms in a bond. But when we are working in chemistry, when we're dealing with substances are made of molecules, and all molecules contain lots of covalent bonds. Well, not all. Some of them only contain one, but most molecules contain lots of different covalent bonds. So what we're going to look at in this section is how we get from this concept of polar bonds to polar molecules. Now, you might think, well, if a molecule has polar bonds, it must also therefore be a polar molecule, right? Well, sort of, but they are not. That's not always the case. So what we are going to look at, so polar bonds do not always mean polar molecules. And what we're going to look at in the next section is how we figure out whether a molecule is polar overall. That is a really, really important point in this topic. So is the molecule polar? That's what we're going to be trying to figure out. That's what we're going to be learning about. And that's really, really important for the whole of the rest of chemistry, because whether the molecule is polar overall affects the type of intermolecular forces. Oh, I'm going to run out of space here. Don't copy this down. You've got your notes on this. You don't need to write this down. So what I'm going to do in the next little section is read through the little section on this in your booklet and try and just explain it in a little bit more detail. Okay, so your notes start with a little introduction to what we mean by a polar molecule. So a polar molecule is a molecule which has a permanent dipole. In other words, there is a slightly positive charge on one side and a slightly negative charge on the other side of the molecule overall, and these charges are permanent. So what we're going to learn about is how to decide whether the molecule is polar. And to determine whether the molecule is polar, overall we must consider two different things. First of all, are there any differences in electronegativity between atoms in any of the bonds? So, if the answer is yes, and we have polar bonds, the molecule might be polar, and we have to move to question 2. If the answer is no, and we've got no non-polar bonds, the molecule must also be non-polar. So I'll just run through a little example of that. So say we have, for example, a molecule, a diatomic molecule, such as the Br2 molecule, bromine. Now, I know already, without even looking up the data booklet, that because I have two atoms of the same type, their electronegativity values must be equal. So if we have two atoms of the same type, then we're going to have definitely non-polar bonds. So there's no polar bonds at all in that molecule, and we're going to have to say the molecule therefore must also be non-polar. If, on the other hand, I had a molecule like water, and I would look at the electronegativity differences for these two atoms. So oxygen is electronegativity of 3.5, hydrogen is an electronegativity of 2.2. So oxygen is quite a lot more electronegative, it's quite a bit more greedy, it steals the electrons from hydrogen. Oxygen is going to become delta negative and hydrogen is going to become delta positive in this bond. So we've got one example of no, we definitely don't have any polar bonds, so the molecule must be non-polar. And then we've got another example where we have, yes, got polar bonds. At this stage, water you'll soon learn about in a bit more detail, but at this stage we can only say the molecule might be polar, and we have to move to question 2. And question 2 says, is the molecule symmetrical? And if the molecule is symmetrical, then the bond dipoles will cancel out and the molecule will be non-polar overall. If the molecule is not symmetrical, then the molecule is polar. And what the rest of this page looks at in a bit more detail is how to tell if the molecule is symmetrical. The word symmetrical can be a little bit misleading in this case though, so I'll just continue with looking at my example of water. So now that we've established that water has polar bonds, we have to ask ourselves, is it symmetrical? Now, this term symmetrical, you could say, yes, well, water is symmetrical down this axis here. This left-hand side is a mirror image of this right-hand side. So I find the term symmetrical a little bit unhelpful here, but that's the term that the SQA use, and it's one that comes up a lot in exam papers. So whilst water is symmetrical on this axis, it's definitely not symmetrical on this axis. And because we have a delta minus up here and 2 delta pluses down here, hopefully you can see that we're going to end up with one side, this kind of, you could say on the page, the top side of the water molecule is overall slightly negative, and the bottom side, the side of the water molecule with 2 hydrogens, because these both have a positive charge, this bottom part is going to be positive overall. So water is not symmetrical, it has polar bonds. It is not symmetrical. So when you're looking at symmetry, you kind of need to think about it in terms of a few of different axes of symmetry, but we're going to look at some specific examples, and therefore it is a polar molecule. Okay, so like I say, I don't think the term symmetrical is particularly helpful here. to be honest, most of the molecules you come across which have polar bonds will probably be polar overall, but there's just a couple of examples that you really need to know where we might have polar bonds in a molecule, but the molecule would be non-polar overall. So I would recommend that you learn these two examples, and we'll just have to look at them together because it's quite hard for me to cover up the page. So there's two examples here on this page where we have polar bonds, but we have what we call a symmetrical molecule, and that leads to the polarity cancel out, and I'll explain that in a bit more detail in a minute. So the first example is carbon dioxide. We can tell that that definitely has polar bonds if we look at the electronegativity values. So carbon, I think, is 2.5, and oxygen, like we said before, has an electronegativity value of 3.5. So the oxygens are definitely going to hog the electrons a bit. We are going to end up with these, with a delta plus carbon and delta minus oxygens. But then we've got to look at the shape of the molecule, and I think it helps, rather than, well, as well as thinking about symmetry, I think it really helps. It helps me a lot in this case to visualise it, to consider the fact that these bond dipoles are vector quantities. They're actually also known as bond moments. Now, you won't be asked about anything about vectors in this topic, but just for me, I think it's a helpful way of looking at it. So I'm going to show you how, if we consider these bond dipoles as vectors, how the symmetry of carbon dioxide leads to the bond dipoles cancelling out and the molecule being non-polar overall. Okay, so we're just going to go through the process of figuring out, is carbon dioxide a polar molecule? So first of all, we have to consider whether there are polar bonds present, and for that we have to look at electronegativity. So we can see that there is a difference in electronegativity. That means we are going to have polar bonds. So that was kind of question one of my little process. We do have polar bonds, so we're going to move on to question two, which is it symmetrical? Because if it's symmetrical, then the bond dipoles will cancel out. Now, this is one of my examples of something that is symmetrical, and I'm just going to explain to you how it's symmetrical and how the dipoles cancel out. Well, first of all, you can imagine the lines of symmetry. So you can imagine the fact that carbon dioxide is symmetrical both in this plane and in this plane. So it does look a bit more symmetrical than our water example, but it helps to look at the dipoles. So what we have is we can draw the dipoles, the bond dipoles, using these arrows. And remember, the arrows always point from the positive to the negative. And if we think about these as vectors, hopefully you will know from maths that when we add two vectors, like imagine if, I'm going to draw a wee compass over here. Okay, so this is north, east, south and west. Right, if we were adding two vectors of distance, if we had someone travelling northeast and then west, we would add the vectors from what we say tip to tail. So we always line up the arrows from the tip of the arrow to the tail of the arrow, and therefore if someone has walked this distance northeast and then this distance west, actually what's happened is that they've gone due north overall. So that's what we're thinking about with these dipole arrows. So if we've got an arrow, if we're adding these two as vectors and we've got an arrow pointing in this direction and we add it from tip to tail with the arrow pointing in this direction, hopefully you can see that those two vectors, because they're equal in proportion, they would just add up to 0. Because if we go from the middle out to here and then we add this one and we go back again, we are ending up with a 0 vector overall. So in this case, what we would see is that even though we've got two bond dipoles, we would say that the bond dipoles cancel out. And the key word, again, at higher there are these keywords that don't necessarily work that well with the explanations. Well, they do, but these keywords that lead you to picking up the marks in this type of question. So the keyword you want to get in here with carbon dioxide is symmetry. So the bond dipoles cancel out due to symmetry, and the molecule is non-polar overall. Okay, so the other example that I've given you in your notes of a molecule that has polar bonds but is symmetrical, so ends up being non-polar overall, is carbon tetrachloride. So actually any structure which is tetrahedral and has 4 of the same atom round about the central atom is going to be what we call symmetrical and non-polar overall. Now again, we can visualise this using the vectors, but it actually doesn't work out so well because we have to draw the tetrahedron in 2D. So when we do this in 2D and we try and add our vectors tip to tail, it doesn't quite work. But if you do look at the 3D structure of this molecule and consider each of the bond dipole vectors and try and add them up. Now, this isn't going to work that well in the video, but you can convince yourself that this indeed is symmetrical and all of the bond dipoles would add up to 0. So if I'm trying to add my vectors tip to tail, I would go like that. This one would be here. My next one, lining up with this bond, would go here. And if you lined up the final vector, you would see, and I know it's really difficult to see in terms of vectors with the tetrahedral shape, but you would see that all 4 of the bond dipoles would cancel out. And again, you can consider how a tetrahedron has rotational symmetry in quite a few different directions, so it is actually quite a highly symmetrical structure. We've got rotational symmetry in lots of different axes here. So those are the 2 examples that you need to know of shapes of molecule that, even if the bonds are polar, even if we have these individual bond dipoles, the dipoles cancel out and there is no net molecular dipole. On the next page here, I've got a couple of examples for you, just to illustrate a couple of examples where the structures would be polar, the bond dipoles don't cancel out, and hopefully that will make sense when you look at it, if you think about it in terms of vectors as well. So these structures are not symmetrical. Like I say, most of the structures you'll come across probably aren't symmetrical, and that's why I would recommend that you really learn these 2 examples, and then you can just, there's a very small chance a different symmetrical structure might come up, but these are the 2 main ones we come across. So the task for this section is for you to look at the shapes of 6 different molecules and try and work out whether they are polar or non-polar by drawing on the 3D shapes of the molecules, drawing in any delta negatives or delta positives where appropriate, and also drawing in bond dipole arrows. So for each one, you're going to just need to draw out the shape of the molecule. So the first 2 are quite easy because they're both linear. I'm going to leave you to either know the shapes of these other ones or just to Google it if you're really stuck. So you're going to draw the shape. You're then going to write on the electronegativity values. Bromine, well, I don't need to do that for bromine because they're the same. So I went through that already, so this one's definitely non-polar. HCl, though hydrogen's got an electronegativity of 2.2, chlorine has an electronegativity of 3.0. So we're going to have delta minus here, delta plus here, because the more electronegative atom is going to hog the electrons and become slightly negative. So we've got our bonds dipole, because there's only one dipole in this molecule, and because it's only a diatomic molecule but with 2 different atoms, it's definitely not symmetrical. So this one is definitely going to be polar overall. So for each of these examples, you've got to look at the shape, you've got to look at any bonds dipoles, and then you've got to look at whether the molecule is symmetrical or not and decide whether they are polar or non-polar molecules. Hope you get on okay with this. Any questions, just let me know. I just want to highlight one little bit of the notes which I didn't emphasise when I was going through them here. So when we're looking at structures and deciding whether they are polar, when we're looking at molecules and deciding whether they're polar or non-polar overall, something that's important and worth considering is quite often, very often in chemistry, we're dealing with molecules with carbon and hydrogen in them. Now, the electronegativity difference between carbon and hydrogen is relatively small. So hydrogen's got an electronegativity of 2.2, carbon is 2.5. So that difference is 0.3 overall. Now, it is quite small, and if you look back to the page on bonding continuum, you'll see that 0.3 is about the threshold for whether we would consider a bond to be polar at all. So partly due to the fact that we've got quite a low electronegativity value difference, and also partly to do with the fact that hydrocarbons tend to have fairly symmetrical structures, we tend to consider carbon-hydrogen bonds as non-polar. I don't want you to just use this value of 0.3 to completely discount polarity though, because sometimes you will see examples where the electronegativity difference is 0.3 and it might be that this molecule would be considered polar. But in general, and the reason we haven't got any symbols on these hydrogen atoms in this diagram, or haven't got any bond dipole vectors on these bonds here, is that we tend to consider carbon-hydrogen bonds as non-polar. And we don't tend to look at them when we're considering whether the molecule is polar overall. And that's quite important because generally our hydrocarbon molecules are non-polar, and we'll see the relevance of that when we come to look at intermolecular forces.